Is the data spatially autocorrelated? Let's figure out.
Let's start running different scripts associated with the omnidirectional semivariogram cloud. Remember that these scripts were created at the second lesson of the third geostatistics course. The first script I would like to run is the number one, and this one is just the regular omnidirectional semivariogram cloud, is this one. And if we open to see the script, edit script, as you can see at the formula here, we are assuming that we have a constant mean. But that's not true, because we are already known that there is a trend on the data. But let's go to see what happened when we try to run this script that is assuming a constant mean, but we have a trend. We are going to work with the data set that will remove the outlier. Can be any of these two, right? Then the parameter of interest is going to be the groundwater. And the cutoff, we are going to take all the extension. It means that we are going to take from here to here, and we can calculate this distance approximately with this tool. Then if we are moving over here, as you can see, we have almost 450,000 meters, okay? That's the distance I'm going to put here for the cutoff. Then it's going to be 450,000. And the label X is going to be the lag distance in meters. The label Y is going to be the semivariance for the groundwater elevation in meters. Title of the graph is going to be the omnidirectional semivariogram cloud. And the subtitle is going to be raw data. Then we can run this script. And double click to open. Let's go to make this screen bigger. Now let's go to analyze this graph. At the x-axis, we have the lag distance in meters, and we have 450,000 meters. Then we have here all the possible data set, okay? All the pair of samples are located in this graph because we took all the extension. Then we have all the data set represented in that graph, in this graph over here. At the y-axis, we have the semivariance for the groundwater elevation in meters. And what we can see here, that is pretty clear, that the data is showing a trend. As you can see, the dots are showing a specific direction, and it is this direction, right? And this one, it's indicating that we can use also the omnidirectional semivariogram cloud to identify trend on the data, because that's what we can see here, that there is a trend. We don't have a cloud of points where the data is showing, you know, totally randomly, and there is no clear direction. But in this case, it is evident that the dots are showing a direction, and that's the important thing. Then we can say that we can use the omnidirectional semivariogram cloud to identify trend on the data. And also, as we are going to see later, we can use also the experimental semivariogram to identify that trend. Then, as we have a trend on the data, we cannot use that data to do the ordinary Kriging. Remember that when we are working with universal Kriging, we have two different terms. One term is the deterministic part, and that's the trend, and the other part is the stochastic part, and the stochastic part is the ordinary Kriging. Then when we plus these two things together, what we are going to have is the universal Kriging, right? But when we are using the constant mean, as we are using in this graph, we are assuming that the data doesn't have trend, but that is not the case, because as you can see, we have a trend. Then we have to use a different script that removes the trend from the data automatically and provides the omnidirectional semivariogram cloud of the residuals, right? And that's the script that we are going to use now. Then that one is going to be the script number 3. And let me show you the formula, edit script. And as you can see in this formula, what we are doing is assuming that the independent variable, that is the groundwater elevation, is depending on the x and y. And with this formula, the software R is going to remove the trend from the data and is going to provide us the omnidirectional semivariogram cloud for the residuals when it's removing the first order trend surface. Okay, this one is the first order trend surface. And let's go to see what happened then. Then double click to open. And as you can see here, it is pretty similar to the other script. We are going to select this one. The parameter again is going to be the groundwater, because that's the advantage of using universal Kriging, right? That you have not to work separately with the deterministic part and with the stochastic part. You can use one script to work with everything together. That's the reason, because we are selecting the groundwater and we are not selecting the residual, right? Because the software is doing everything automatically. Then the parameter independent A is going to be the X, that is the X coordinates. The B is going to be the Y coordinates. And for the rest of the things are going to be the same. I'm going to copy and paste. But for the subtitle, what I'm going to add is residuals for first order trend surface. Now we can run this script. And double click to open. Now, as you can see, we don't have any trend. That's what I was saying previously, right? The data looks pretty randomly distributed and you cannot see a specific direction as we can see in this graph over here, right? Again, we have all the data points on this graph because we are covering all the extension, but this data now is associated with the residuals from the first order trend surface. And as you can see, we didn't provide any residual values. The software did that one automatically. When we are using this script, the software is giving us the residual values automatically from the first order trend surface, right? But it is interesting that now, for example, if we took this one again and instead to use the groundwater, we are taking this one, we are going to get the same results. Because as we already know, the residual values that we calculated at the attribute table, let me show you here, open, these values over here for the first order, right? That's the residual values. If we take these values now and we did the omnidirectional semivariogram cloud, assuming that we have a constant mean, we are going to have the same results here and here. Let me run this script. Double click to open. And let's go to make this one bigger. And if we compare this one with this one, you can see that we have identical results. Okay, but when we are using this script that removes automatically the first order trend surface, we didn't add any residual values because what we are adding is the groundwater elevation. That's the advantage of universal Kriging, right? That the script removes the trend from the data and provides the residuals directly. And that's the thing I want to show you when we are using this script, right? And now we are going to do the same, but for the second order trend surface. And that script is the number 4. this one over here. Let me show you the formula. And here you have the formula for a second order trend surface, right? Now we are saying that the groundwater elevation is depending in all these variables over here. And let's go to run that script, then execute. Put over here, we are going to use this data set. The parameter dependent is going to be the groundwater. The parameters independent are going to be the y and x. The cutoff is 450 meters, 450,000 meters. And I'm going to copy and paste the labels. In this case, the subtitle is going to be residual second order trend surface. Then we can run this script. And double click to open. Let's go to make this screen bigger. I can remove this one. Then what we have here is the residuals from the second order trend surface. And again, as you can see, there is no trend on the data. Then at the end, we have three different graphs. The first graph is the raw data, where we can see that there is a trend. Then the second graph is the residual values when we remove the first order trend surface. And the third graph is the residual values when we remove the second order trend surface. Using these scripts, we can work directly with the residuals without calculating them. But that is not the truth, right? Because we need to calculate the residuals in order to know if we have a regression model that is valid. Then at the end, we cannot avoid to calculate the residuals. But as you can see, when we are using these scripts, we don't need to calculate it because we are going to have results without any calculation. The software is doing that job automatically. Also, I would like to tell you that if you want to get this data, any of these data sets, to do your own graphs, for example, with Excel, I created some scripts to extract the data from these graphs, right? And that scripts are these ones over here, right? For example, number 6, Semivariogram cloud data table, the trend, first order trend surface. It means with this script, number 6, then you can fill the information over here and you can save the stacks, right? And then you are going to have the data for the first order trend surface. You are going to have the lag distance and also the semivariance for the groundwater elevation for each of these dogs. Then if you want to have that data to manipulate the graph in a different software, you can do that one also, right? And there are different scripts. You can do that one for the first order. This one is for the second order. This one is a directional semivariogram cloud if you want to add any specific direction in the bin. And this one is for to have the data when it's directional semivariogram cloud for the first order trend surface. You can get also the data. There are a lot of scripts. We are not going to use all of them, but as I said, you can watch the video tutorial at the second lesson of the third geostatistics course. Now I'm going to close all these ones and we are going to run the omnidirectional experimental semivariogram, and that one is going to be the script number 10. Double click to open, and this script and the next that we are going to use was created at the lesson number 4th of the third geostatistics course. Then if you want to implement these scripts on your QGIS, just follow that video tutorial in order to download the scripts. Then in this one, we are going to select the proper vector file, is this one. The parameter again is going to be the groundwater. Cutoff we are going to take the maximum extension. For the lag distance, at the moment, we are going to put 45,000. And X is going to be lag distance. I'm going to add the labels, but I'm going to pass the video faster. I added already all the labels. Remember that this one is the omnidirectional experimental semivariogram, but as you can see here at the formula, again, we are assuming that we have a constant mean, but that's not true, right? Because we know already that there is a trend. But in this case, you are going to see how we can use the omnidirectional experimental semivariogram to identify also the trend on the data. Let's go to run this one. And double click to open. And let's go to make the screen bigger. And as you can see, what we have is a quadratic behavior of the data. When you have this type of shape on the lag distance, for the dots of the lag distance, it is indicating that we have a trend on the data. Then you cannot use a constant mean when you have something like that. Then we have to remove again the trend from the data. And remember that we get this graph from this data over here, okay? But what we are doing now is a lag distance of 45,000 meters, right? Then it's taking an average and giving this point over here. Then from here, we get this one. Then as we know that we cannot use this data to do the omnidirectional experimental semivariogram, we are going to see a script that removes the first order trend surface from the data and provides the omnidirectional experimental semivariogram after removing the first order trend surface. Then that one is going to be the script number 12. As you can see, omnidirectional experimental semivariogram, first order trend surface with the variance. And number 13, let me see number 13, second order. Okay, maybe for this one we can have the variance on the graph because I added the variance, okay? Then let's go to select this one. The parameter that is dependent is the groundwater. The independent parameters are the X and Y. Then I'm going to copy the labels, but I'm going to pass the video faster. I added all the information. Now we can run this script. Double click to open, and let's go to make this screen bigger. Important things here, okay? We are working with the residuals from the first order trend surface. Remember that if we go here, is this script. If we open edit script, we are going to see what is, not this one, number 12. Edit the script. We are going to see that we are working with this formula, okay? That formula provides the residuals from the first order trend surface. And that's what we have in this graph. Another important thing, the data presents a structure, because as you can see, we are going up, then reach this point and then go down. We don't have a quadratic behavior of the data. We reach a seal. It is indicating that the data has a structure. Then if the data has a structure, we can apply the ordinary Kriging. Because as you can see, the nugget effect that maybe is over here, compared with the partial seal, it's very small, okay? The nugget effect compared with the partial seal is very small. That is a good structure of the data. Other important thing, for this graph, we have the variance. The variance is approximately where we are going to have the seal of the data, okay? The seal is going to be around this area over here. Most important things also, the range. The range is going to be approximately 100,000 because it's more or less where we are going to reach the seal, okay, is this distance over here. It's going to be around over here, the range of our data. And that's the information that we are going to add at the next scripts to have the graph of the omnidirectional experimental semivariogram to fit the model. Because as you already know, the correlated area of the graph is where we have the range, okay? Then after the range is going to be the uncorrelated area, and it's going to be all this area, and we don't want this data. The data that we want to fit the model on the experimental semivariogram is going to be the data that is correlated, and that correlated area is where we have the range, okay? And it's going to be more or less until here. But the point is that we need more data points over here to fit better the model, right? Then what we are going to do is create a new omnidirectional experimental semivariogram with this range and more data points over here. But that one is going to be later. Now we are going to do the same graph, but for the second order trend surface, for the residuals. In that graph, we are not going to add the variance. You know, this kind of things is things that you can add in R to have the graphs that you want, right? And as I explained previously, you can modify the scripts as you want, you know, with the colors, with the legends. It's up to you with the title. Everything can be changed in this graph, okay? That's the scripts I created, but you can make your own scripts. You can use this script as the base, and then you can modify whatever you want to have the things that you need, okay? In the next script is going to be number 13, is this one, and I'm going to add the information, but I'm going to pass the video faster. I already added all the information. This one is going to be the residuals for the second order trend surface. Remember, if we check here the formula, we are going to see that now we are saying that the groundwater elevation is depending on all these parameters, okay? Then we can run this script. Double click to open and make this screen bigger. Remember that we are analyzing the first order and also the second order because we want to make sure that both of them present a correlated area and they have a good structure, okay? Because if some of them have no good structure or has not present a correlated area, we cannot do ordinary Kriging, right? Then we want to make sure that we can use any of them to do the Kriging interpolation, right? Then again, this graph has good structure. The data has good structure because you can see it's growing up, then go down over here, right? Then the nugget effect that maybe is over here is going to be very small compared with the partial seal. Again, that is indicating good structure. The range is approximately the same as before, you know, 100,000 meters. And honestly, there is not too much differences between the second order trend surface and the first order trend surface. They present pretty similar structure. And remember that this second order trend surface data comes from this graph over here. And this one, that is the first order trend surface, it comes from this graph over here, okay? That one and that one is just an average according to the lag distance that we added here at the parameter for the lag, okay? Now the next step is to create the omnidirectional experimental semivariogram more accurate, okay? Because what we did here is the omnidirectional experimental semivariogram for all the extension, for both of them, for the first order trend surface and for the second order trend surface. But we don't want that one because we want to work just at the correlated area of the graph. Then we are going to make the representation of the omnidirectional experimental semivariogram, but just until, for example, 150,000 meters. Then in that way, we are going to guarantee that we have the representation of the correlated area. And we are going to do that one for both of them, for the first order trend surface and for the second order trend surface. Then let's go to start with the first order trend surface. Then here we are going to leave the same parameters, but now for the cutoff we are going to add 150,000. And for the lag distance we are going to add 15,000. Because we want to have at least 10 lags to fit the model on the experimental semivariogram. And we can run now this script and to see how it looks like. Then double click to open, and let's go to make this screen bigger. And again, as you can see, we have that the experimental semivariogram is growing up, and then over here approximately it reaches the seal and then go down. Then for this lag distance, it's good to make the representation of the just of the correlated area. Now we're going to do the same, but for the second order trend surface. Then is this one, I believe, second order trend surface. We are going to add 150,000 and 15,000. And then we can run this one. And see how it looks like. Double click to open. And also in this case, we can see that we are covering the correlated area of the graph. Then we are going to use this lag distance to fit the model. And also other interesting thing is that now each lag has less pair of samples, as you can see, okay? If you compare with the one that we did with all the extension, for example, for the first order trend surface is this one, and here you can see that we have lag with 287, 373, but now as the lag distance is smaller than before, because before we put 45,000 and now we are putting 15,000, the number of pairs for each lag is less, as you can see over here, right? 59, 91, any number over 100 is going to be pretty representative, okay? And for these two values over here, even for this one, there is not too much pair of samples, but that's what we have, and that's the data what we have to use to work on, right? And the same happened here. We have the same lags distance, and then we have the same number of pair of samples. Now it's time to fit the model, and we are going to use the script number 20. Is this one over here. Remember that this script was created at the lesson 5 of the third geostatistics course. Then if you want to implement this script in your QGIS, just follow that lesson. Then here we're going to select the data for the vector file. Is going to be this one. The parameter of interest and is the dependent is going to be the groundwater. X and Y are the independent parameters. Cutoff, as we say previously, is going to be 150,000. Lag distance is going to be 15,000. This one is not the seal, is the partial seal, and we can add here an approximately value because the fit of the model on the data is going to be automatic, but we can add here an approximately values, okay? Then for the partial seal, we can see that it's going to be around, if the seal maybe, if the nugget maybe is 1,000, the seal is going to be about 2,500 or something like that, okay? Then we can add here, for example, 3000. The model, we can try the spherical one. Then the range, we can check here the range also approximately. Could be maybe I'm going to add 100,000. Niagara effect, as I said previously, I'm going to add 1000. For the X is going to be the same label as this one. X, I'm going to copy and paste. For the title, I'm going to add the same as this one, copy, but I'm going to add at the beginning model. Model, omnidirectional experimental semivariogram. And for subtitle, I'm going to add this one, copy. But here also at the beginning, I'm going to add a spherical. Spherical model, omnidirectional semivariogram curve, and I can semivariogram, and I'm going to add here a point. Then we can run this one. And here we are going to have the parameters for the model. Okay, then we have a Niagara effect. That's the Niagara effect. Is 1,170 meters. We have the partial seal, that is almost 3,000. And we have the range here, that is almost 150,000 meters. Then we can open and make this screen bigger. And what we can see here is that the title doesn't fit really well. Then here we have a couple of options. We can edit the script to change the size of these letters, or maybe change the title. And also I make a mistake here because that one is related with the residuals from the first order train surface. Then I'm going to fix that things. Here, this one is going to be first order. And also here I'm going to remove the spherical model from here, cut, and I'm going to add over here. Paste, and that's it. I'm going to give an space. And I'm going to run this script again. Then double click to open. I don't want this one, and I'm going to make this screen bigger. And that's how the software fit the model on the omnidirectional experimental semivariogram in an automatic way, okay? But if you want to fit the model manually, I have a specific script, and that one is the number 28, I believe. Let me check. Yes, 28 is this script over here, 28, where you can fit the model manually, as you can see on the title. And this one is for the omnidirectional first order train surface, for the omnidirectional experimental semivariogram from the residuals from the first order train surface. Okay, we are not going to use this one because I believe the automatic fit is good, and we are going to work with this spherical model. Also here you can change if you want to try different models. For example, you can add here the exponential, but then also you have to change the title over here for exponential. And you can check how it looks like. Double click to open. Let's go to make this one bigger. That one is for the exponential. But the spherical is pretty good, right? And also here we have the values for the exponential model. We have an aggregate effect of 1100, a partial seal of 4400, and a range of 1100,000. And also we can run, for example, the Gaussian model. Run, and we can change also here. That's the models I add to the script, but you can add more models if you want, right? That's the most common ones. Here we have the parameters, and double click to open. But this one doesn't look really good, right? I'm going to make bigger even. For me, the best model is going to be something between the spherical and the exponential, but I am going to use the what happened here? I'm going to use the spherical model. Would like to add this one here. I don't know if I can do that one. Right here. Okay. Then now we are going to do the same, but for the second order train surface. We have to create the script for the second order train surface for fitting the model because I didn't make it, okay? Then what we are going to do is copy the formula from here, edit the script. It's going to be this formula. That's for the second order train surface. Copy. Close this one and go to the 20. That's for fitting the model. Edit the script. And here for the formula, we have just for the first order. Then I'm going to change this formula. Paste. But the script is going to be all the same. The only thing is changing is the formula, right? Then I'm going to save this one as a number 20B. Not this one. This one. Here is going to be second order. And it's going to be 20B. Save and close. And now let's go to run that script. Structural number 20B. Double click to open. We are going to add here the layer is this one. Groundwater X, Y. I'm going to copy and paste all the parameters from here to here, but I'm going to pass the video faster. Well, I added everything. As you can see, the cutoff is going to be the same as before, 150,000, lag distance 15,000. The partial seal, the value is approximately because again, the model is going to be fit automatically on the data. The model is going to be the spherical, the range approximately 100,000, nag effect 1,000. The label for X is going to be the lag distance. The label for Y is going to be the semivariance for the groundwater elevation in meters. Remember that is for the residual values. The title of the graph is going to be omnidirectional experimental semivariogram, and for the subtitle is going to be a spherical model for the residual second order train surface. Then we can run now this script. Okay, here we have a problem with one of the parameters. Let me edit this one. And the problem here is that we have to add here like this one. Then it's going to be Z, this one is going to be X, this one is going to be Y, this one is going to be X, Y, X, and Y. Let's see if now it works. Save, close, and let's go to run this one again. And double click to open, and let's go to make this screen bigger. And that's the model, right, for the residuals for the second order trend surface and spherical model. Then we can compare this one with this one, that is from the first order trend surface, and this one is for the second order trend surface. And also we can check the parameters for the model are these ones. Then here we have a nugget effect that is 1000, almost 300 meters. The partial seal is 1700 meters, and the range is almost a little bit more than 100,000. Now the next step is to see how good is the model, and we are going to compare the model from the first order trend surface and the model from the second order trend surface, both of them spherical model.